Have you ever imagined a world where electricity doesn't come from coal, oil, or even traditional nuclear power, but from something far more powerful, cleaner, and virtually limitless? Well, this isn't science fiction anymore. China has sworn to reshape the future of global energy with a groundbreaking plan to build the world's first nuclear fusion power plant by 2030. But what does that really mean? And why should we care? In my opinion, this isn't just about power. This is about a global energy revolution, a shift that could change how the world lives, works, and survives. Recently, the tech world was electrified by China's bold announcement: the construction of a commercial nuclear fusion plant set to go live by the end of this decade. This isn't some scene from a sci-fi blockbuster. This is real, and it's happening now. If successful, it could completely rewrite our energy landscape. Imagine a future where fossil fuels are obsolete, where we no longer worry about nuclear waste piling up, and where energy is clean, abundant, and sustainable for generations. That's the promise of nuclear fusion. So, what exactly is nuclear fusion? Well, let's start with what we already know. Most of today's nuclear power comes from fission-splitting heavy atomic nuclei like uranium. That process releases energy, but also creates long-lived radioactive waste. Fusion is the opposite. It mimics what powers the sun. Two light nuclei, like isotopes of hydrogen, deuterium, and tritium, fuse together under intense heat and pressure to form a heavier nucleus, releasing a massive burst of energy in the process. And just how powerful is it? To put it simply, 1 gram of fusion fuel can release over 40 times the energy of fission. And compared to fossil fuels, the energy density is over 100,000 times greater. That's not just impressive, that's revolutionary. Now you might ask, is it really that clean? The answer is yes, remarkably clean. Fusion produces no greenhouse gases during operation. It creates no long-term radioactive waste, unlike fission. And its raw materials? They're abundant. Deuterium can be extracted from seawater, and tritium can be bred from lithium found in the Earth's crust. We're talking hundreds of millions of years worth of supply. Compare that to coal, oil, or gas, which are not only dirty but rapidly depleting, and the choice becomes obvious. So, if it's so perfect, why haven't we done this already? Well, here's the catch. To trigger fusion, you need extreme conditions. We're talking about temperatures of 100 million to 1.5 billion degrees Celsius. That's hotter than the core of the Sunday. Why so hot? Because hydrogen nuclei naturally repel each other. Only at these extreme temperatures can they gain enough energy to overcome this repulsion and fuse. On top of that, you need enormous pressure, and you have to confine the hot plasma long enough for fusion to occur. To do this, scientists use devices like tokamaks, which use powerful superconducting magnets to trap the plasma inside a donut-shaped chamber, keeping it from touching and damaging the reactor walls. China has been quietly laying the groundwork for decades. From building a series of experimental devices to developing cutting-edge superconducting technologies, they've steadily moved closer to practical fusion power. Take the East reactor, often called the artificial sun. In 2024, it achieved a world record by maintaining controlled fusion for over 400 seconds. Now, all eyes are on Project Spark, a hybrid fusion-fission reactor under construction on Yaohu Lake Science Island in Jiangxi Province. Backed by a massive 20 billion yuan investment, Spark aims to generate 100 megawatts of power and feed it directly into China's national grid by 2030. And that's just phase 1. But China isn't alone in the race. The US has launched a federal fusion initiative targeting 400 megawatts of power in the early 2030 seconds. Germany, Japan, and a consortium of 35 countries are building the massive ITER reactor in France. Yet, despite all this global effort, none of these projects are expected to reach commercial output before China's Spark. In terms of performance, Spark is aiming for a Q value that's the ratio of energy output to input of over 30. For context, a Q value of just 10 is considered a major breakthrough. If China hits this target, it would be a leap ahead of everyone else. Of course, challenges remain. Technologically, we still need better materials, ones that can withstand extreme heat and neutron bombardment. We also need more stable plasma control, improved superconductors, and smarter energy conversion systems. From an engineering standpoint, building a fusion plant is a monumental task. It requires advanced skills, massive coordination, and long-term investment. But here's the thing. China has shown remarkable consistency in hitting milestones that once seemed impossible. And with strong state support, world-class research teams, and growing international interest, this fusion dream might finally become reality. So, what does this mean? In my opinion, we're not just witnessing a new type of power plant. We're watching the birth of an entirely new energy era. If fusion can be mastered and commercialized, it could power our cities, industries, and technologies without destroying the planet. By 2030, China may not just turn on a new power station, it may ignite a global transformation. Let's stay tuned and see if the world's first true artificial sun will rise in the east.